What is pairing heap? So pairing heaps are the specific implementation of a heap data structure. These are self-adjusting structures which rearrange themselves when operations happen to remain balanced. For example, aviary tree. Friedman and Tarzan, they invented an efficient form of heap called Fibonacci heap. Though theoretically efficient, but it was complex to implement and not as fast as other heaps. So pairing heap is intended to be a competitive of Fibonacci heap in theory, and it is easy to implement and fast in practice. What are the applications? Well, it is efficient implementation of priority queue. They are faster than binary heap and Fibonacci heap. They have least time complexity in most of the operations. We'll see later on. And they can be used as an efficient way for implementing digits rather than minimum spanning tree algorithms. So now let us look at the structure of heap. Pairing heaps, they maintain a min heap property that all parent node to always have a smaller value than their children, and they also maintain max heap property if the pairing heap is a max heap. Well, each node keeps a track of following information: a pointer to its leftmost child node and a pointer to its sibling nodes, and the pointers in the pairing heap are shown. So here we see that there is a heap which is a min heap because the root node or the parent node has lesser value than the child nodes. And here on the right side we see a diagram in which is a representation of pairing heap where the root node is connected to the leftmost child node and then they are connected to its siblings. So now let us look at the operations. So here is how pairing heaps, they implement the basic functionalities of heaps and the time complexity of each operation. And these operations, they describe a min pairing heap, but it could be easily arranged to work for max pairing heaps. So in a pairing heap, finding the minimum element is very simple. Just return the top of the element. So here is the algorithm, and the time complexity is big O of 1. So in this algorithm, you see if top is empty, then it's an error or you don't return anything, else you just return the top element because it is a min heap property. We just assume that it follows a min heap property. So the parent node or the root node would have the minimum value. Okay, so moving on to the next operation, which is merge, or sometimes called meld. So if merging occurs between non-empty pairing heap and an empty pairing heap, merge just returns the non-empty pairing heap. If both pairing heaps are non-empty, then merge function returns a new heap where the smallest root of the two heaps is the root of the new combined heap and adds the other heap to the list of sub-heaps. The time complexity is big O of 1. So as you can see in the next diagram, we have two heaps A and B. While comparing the root elements of both of the heaps, we find that A has a larger value, or say greater than B. So A would be the root of the new heap, and B, the root of B, that is 20, would be combined to the root of A, and then we would attach the A's old subtree as a right child and followed by the B. So this is how the merge takes place, again repeating the time complexity is big O of 1. And this is the algorithm for the merge, or you can say the meld operation. Inserting. So inserting an element is like merging the element with the heap. So here's an example which does not violate the min heap property. So to join the two heap, we first compare the root node of the heap. If the root node of the first heap is smaller than the root node of the second, then the root node of the second heap becomes the left child of the first heap, otherwise vice versa. And so the overall time complexity is big O of 1. So as you can see, since 3 is greater than 2, so it becomes the child, I would say leftmost child of the root node. So if you want to add 1, so since 1 is less than the root node of C, so it would become the root node. Here is a simple implementation. Again, it's just a merge operation. So the next operation is delete. To delete a node n, we first would detach the subtree that is rooted at node n, and then delete n from the tree and merge its subtrees into one subtree using a 2-pass method. We'll see what is 2-pass method later in the slides. Then we would merge the detached subtree with the subtree resulting from the 2-pass. Well, I guess let me explain this to you in a very simpler form. First, delete the links between the root, left child and all the siblings of the left child. Then merge the subtrees that are obtained by detaching the left child and all the siblings by the 2-pass method, and then delete the root node. After that, merge the detached subtrees from left to right in the 1-pass, and then merge the subtrees from right to left to form a new heap without the violation of min heap. This process takes log of n time, where n is the number of nodes. So here is one example where we want to delete 1. So first we delete all the links of the left child, that is the child elements of the parent node which we want to delete. So we see here 8, 2, 9 and all this, and in the second step we'll do the 2-pass pairing and show this the tree with root node 3 and 6, they would merge, and then in the third step again 3 and 7 would merge, and then again in the fourth step 2 and 3 would merge. So in this way we are merging all the elements. In the fifth step we get the final tree left after deletion of 1, and this because we were following the 2-pass scheme, we were not able to we were able to not violate the min heap property, because earlier we assumed that we are working with the min heap. So this was all about delete. So in the pointer form, if you see, we represent it in this manner. Okay, so moving on to the next operation is delete minimum. So in a min heap, the minimum element is the root node of the heap, and to delete this element we have to delete the root node. And if the root had 2 or more subtrees, these must be merged together into a single tree. Because there are no parent pointers, it is more difficult to tell if the deletion will cause a min property violation or not, unlike in other heap implementations. So there are many ways to check if heap violation is occurred or not. One of the simplest method is 2-pass pairing or 2-pass merge. Now as you can see in this slide, we have 2 figures shown. Let's start with the pass 1. So in the pass 1, we would examine the subtree from left to right. I say left to right, and then we would merge the pair of subtrees, reducing the number of subtrees to half. Here we can see that 1 and 2 combines to A. So we merge the pair of subtrees, reducing the number of trees to half. And then in the pass 2, we would start with the rightmost subtree of pass 1, and then would call this tree, followed by merging the remaining subtree right to left into the working tree. So this is all about delete minimum. Here is the algorithm for delete minimum. Moving on to the next operation, that is decrease key. So to decrease the key of the node n, if n is already the root, or if n is a new key that is greater than or equal to its parent, no additional steps are needed. If n is a new key and is less than the value of its parent, to maintain the min heap property, action must be taken to produce a valid heap. So we just do we remove the subtree rooted at n, and then we merge the resulting trees. The time complexity is big O of n. So this is the amortized running time of the pairing heap operations, and this is the crux of running time given. So we see that the find minimum, insert and merge, they have big O of 1 as the running time, whereas the remove, delete minimum and decrease key has big O of log of n time. So this is it. I would like to conclude that pairing heap is a simplified form of Fibonacci heap, and it also maintains the property of min heap, which is parent value is less than its child node values, and it is considered as self-adjusting binomial heap, and each node has a pointer towards its left child, and the left child points towards the next sibling of the child, and we have few operations, and this is very efficient to implement when compared to Fibonacci heap, which is theoretically efficient but not practically possible. Thank you very much.